Hi, I'm Yang, and I'm going to be discussing improved iteration complexities for overconstrained p-norm regression. This is joint work with Arun, Jambulapati, and Arun, Sidford at Stanford. To get started, I just wanted to introduce regression problems in general. The regression problems that we're going to be discussing in this talk are of the following form. For convex functions f, like R to R, so single variable convex functions, in a matrix A, which is n by d, we should think of n being much larger than d. In a vector B in Rn, we want to minimize over all x, that's d-dimensional, the sum of f of the error of ax minus b in the ith coordinate. So basically, we look at ax minus b in the ith coordinate, take those, apply the convex function f to each of them and add. So there's a lot of natural examples. When f of x is a pth power, so example, absolute value x to the p, where p is in 1 to infinity, we call this p-norm regression. An equivalent version is to find a vector y in R to the d, such that ay minus b, p-norm, is the most 1 plus epsilon times the minimum over all x of ax minus b, p-norm. That would be computing an epsilon approximate minimizer to the p-norm regression problem. P equals 2 corresponds to the standard linear regression. And linear regression is equivalent to solving a linear system defined by something like the matrix A, more precisely A transpose times a diagonal matrix D times A. It's equivalent to solving a linear system in that. Also, for different functions f, like f of x is log 1 plus e to the minus x, you get logistic regression and various other regression problems. For the purposes of this talk, we're going to focus on giving high accuracy algorithms. In other words, the dependence on epsilon is logarithmic for p-norm regression and p at least 2. So we're going to focus on this setting, and I'll say a couple words about how our result will apply to some other settings, but this is really the main focus. To measure the complexity of p-norm regression, there's two natural ways. The first way is to measure the iteration complexity. This is the number of linear system solves to A transpose dA for some positive diagonal matrix D that we need to solve the LP regression problem. Additionally, during each iteration, we're allowed to do other simple operations like add things, add vectors, multiply by A, etc. Things that are cheaper than solving the linear system. So this is a natural model to study because it implies parallel complexity, and also in generally leads to faster runtimes. As for what's known, it's known that you can do this in O tilde square root D iterations by work of Lee Sidford on interior point methods, and also O tilde P times n to the p minus 2 over 3p minus 2, which is something like O tilde P n to the 1/3. The other natural model to study is runtime. So how can the runtime be better than just solving a linear system naively every step? Well, in general, for these algorithms, the linear systems between steps are very related. And this is kind of true for any algorithm that will try to solve the problem is A transpose dA, where D is a changing diagonal matrix. So to improve the runtime, we will often design data structures for matrices that more efficiently solve linear systems at future iterations given the information of previous iterations. Basically solve it more efficiently than just resolving the linear system every step. In these directions, the dream runtime for p-norm regression problems would be something like nnza plus d to the omega, where omega is the matrix multiplication constant. The reason this is kind of the optimistic runtime is because this seems to be the runtime necessary to solve a single linear system, which is kind of necessary for regression problems. Such a result is only known for p equals 2 for solving a single linear system, or when n is d basically, and then such a result is also known. For the purposes of this talk, we're going to focus on iteration complexity. The reason for this is that it simplifies a lot of the presentation, and oftentimes iteration complexity will imply faster runtimes using the various work that's been done on data structures for inverse maintenance or reducing the iteration cost that have recently been developed. Our results in the context of iteration complexity are that we give an algorithm which runs in p d to the p minus 2 over 3p minus 2 iterations for p-norm regression for p greater than 2. This is a natural combination of the results of the Sidford, which ran in O tilde square root d iterations, and O tilde p n to the p minus 2 over 3p minus 2, which is like np to the 1/3 due to AKPS. As a corollary, we derive that you can solve epsilon approximate L infinity regression with a polynomial dependence on epsilon, d to the 1/3 over epsilon to the 2/3. This is for approximate L infinity regression. Additionally, our results should extend to general quasi-self-concordant optimization, for example, logistic regression, and this will follow from some work of ABS. Also, while p less than 2 is not the focus of the talk, I should mention that we do derive some results for p less than 2. For p less than 2, it's useful to let q be the dual norm of p, so that q is greater than 2. In this setting, we give an algorithm that has q d to the q minus 2 over 2q minus 2 iterations for q norm regression. So in this sense, our iteration cost is actually closer to q times square root d instead of q times d to the 1/3. And it's an interesting open problem to get something that looks more like q d to the 1/3 for the case p less than 2. So let me give some intuition for the previous runtimes for LP regression and how we get a runtime that looks like d to the 1/3. So the intuition I want to give is that, well, we want to solve LP norm regression, and we want to reduce it to solving linear systems. Linear systems are L2 regression. So we want to somehow relate the geometry of the LP norm ball to the L2 norm ball. So more precisely, if A is the input matrix, we might want to say that we want to find a diagonal scaling D such that the AX P norm ball is at most DAX, the 2 norm ball, at most kappa times AX P norm. And we want to kind of minimize kappa. And if you can do that, then, well, we're doing, generally smaller kappa lead to faster runtimes, because that means we're doing a better job of approximating the P norm ball with the 2 norm ball, so we make more progress during each iteration. It is easy to get a bound like kappa equals root n, or something like kappa is n to the 1/2 minus 1 over p. This is achieved when D equals the identity matrix I. So then the bound for kappa would just be what is the distortion between the 2 norm and the LP norm, or in the worst case, the L infinity norm. Because AX, the vector is n-dimensional, the distortion can be all the way up to something like square root n possibly. Such an intuition will end up giving an algorithm with n to the 1/3 iterations. As for where the 1/3 comes from, it's been seen to come from either with reduction ideas, like multiplicative weights and with reduction, introduced by CKMST in 2011, or more recently also done for p-norm regression precisely by AKPW. Also more recently, it's been seen to be kind of equivalent or similar to acceleration. Some work. So I guess now I'm going to talk about why we should expect that you can actually reduce this kappa term and how we get our faster runtime. So once again, remember that our goal is to relate the LP norm ball to a weighted L2 ball, because an L2 ball is like a linear system. On the previous slide, I mentioned that you can actually get kappa is root n. But here I'm actually going to try to explain why kappa equals square root d is possible, square root of the dimension. So intuitively, the reason is because of something called a John's theorem. So John's theorem says that every symmetric convex body is within a square root d distortion of an ellipse. An ellipse is some weighted L2 ball. So let's just do the p equals infinity case as an example. So ax infinity in most one is some symmetric polytope. So let's think of rectangle. This is some rectangle in d dimensions. For this rectangle, we can find some two ellipses which sandwich the rectangle, and their distortion is square root d, where d is the dimension. So we should expect that you can construct these ellipses that kind of sandwich the LP norm, and the distortion is only square root d actually, instead of the square root n that's achieved. And then optimistically, if such a construction is compatible with the previous width reduction or acceleration techniques, then you can get a d to the 1/3 runtime. So that's kind of what I'm going to be explaining why it's possible now. Like, how do we choose d, this diagonal matrix d, to get a square root d sandwiching instead of a square root n sandwiching? So the way to choose such a diagonal matrix d, to get kappa is d to the 1/2 minus 1/p, is using some object called LP norm Lewis weights. So the P norm Lewis weights, which were defined by Lewis and have seen a lot of use in subsampling regression problems in the past, they're defined the following way. The Lewis weights are the unique weights W. In their positive weights, there's n of them. You should think that there's one weight per kind of row of the matrix A, of which there's n of them. They satisfy the following equation: Wi equals Wi to the 1-2/p times AI transpose, and then the inverse of the ellipse A transpose W to the 1-2/p A, the inverse of that matrix, times AI. So you can show that there's a unique set of weights that satisfies this equation, and we call those the LP norm Lewis weights. Here in this equation, W is the diagonal matrix consisting of Lewis weights, and AI is the ith row of the matrix. While Lewis weights have seen a lot of use in p-norm regression in the past, those methods were generally by doing something like sparsification or subspace embeddings, something like that to give an improvement. We believe that the way we're using Lewis weights is fundamentally different from these previous approaches that are more sparsification based. And I'll try to get into the kind of differences a little later. So I gave a formal definition of Lewis weights, but maybe let me just state the important properties that we need about the Lewis weights that will explain why they will give us a nice reweighting of AX that is a good approximation of the LP norm. So the two properties we need are the Lewis weights sum to D instead of N. So the Lewis weights will all be between 0 and 1. You can show that. And in fact, they sum to much less than N, even though they can be at most 1, they sum to D. And also, the Lewis weights give some control over how large the coordinates of AX can be. So formally, the other property we need is that the ith coordinate of the vector AX for any X is at most the Lewis weight Wi to the 1/p power times the L2 norm of W to the 1/2 minus 1/p AX. So these are the two properties we need. Okay. So now, the important lemma is that if the diagonal matrix D is W to the 1/2 minus 1/p, then the induced ellipse is at least AXP norm and at most D to the 1/2 minus 1/p times AXP norm. And this was known previously, but I still want to present a nice proof of it to give some intuition for why these properties of Lewis weights are important. So let's prove the first inequality, that the AXP norm is at most W to the 1/2 minus 1/p AX2. So the proof of this will require the second bullet point under the properties of Lewis weights. To see this, let's write AXP norm to the pth power to be the sum over all coordinates AXI to the p. So out of those AXI to the pth power, pull out AXI to the p minus 2 power and use the second bullet point above. This will give you it's at most W to the 1/2 minus 1/p AX2 norm to the p minus 2, and then times some power of Wi times AXI squared because I removed p minus 2 powers Well, the thing in the sum now is once again, W to the 1/2 minus 1 over P, AX 2 norm squared. So combining everything, we get the desired bound. And then you take a P through to both sides. So yeah, that's why the first inequality is true. So the first inequality is true basically because the Lewis weights give us a bound on how much the ith coordinate can contribute to the total size of AX in some sense. So yeah, let us move on to the second inequality, which is the upper bound. The upper bound simply uses the quality of Lewis weights that they sum to D. So formally, let's just write out what this L2 norm squared is. It's sum Wi to the 1 minus over P, AX squared. And then we use Holder's inequality to get that this is the most Wi to the 1 minus 2 over P times some AXI to the P to the 2 over P. Because the sum of Wi is D, you get D to the 1 minus 2 over P times AX P norm squared. And then you take a square root of both sides. So yeah, the second inequality basically just follows from Holder's inequality. And the condition of the sum of the Lewis weights is MOSD. So that is a proof that I can sandwich the AXP norm with an ellipse, which is just actually reweighting different rows of A up to a D to the 1/2 minus 1 over P factor, instead of the more naive N to the 1/2 minus 1 over P factor. Okay. So let me just touch briefly on how you actually use the Lewis weights in the algorithms. Mostly it is an adaptation of the previous methods, which are either based on this iterative refinement and multiplicative weights and width reduction, or an acceleration framework. In general, for all these methods, every iteration we're going to be solving some problems which have some sort of type of linear term, some quadratic term, and some p-norm term. So for the iterative refinement framework, the precise problem we solve at every iteration are min over all x G transpose x plus x in the norm of A transpose dA plus AX P norm to the P. The intuition is that when we set D to be W to the 1 minus 2 over P power, so like when the ellipse is just like the ellipse given by the Lewis weights in the previous slide, it provides a good enough regularizer for the P norm term, so it will converge kind of quickly. Understanding where the 1/3 comes from involves understanding the width reduction precisely, but it follows similarly to previous ones. Also, similarly in the acceleration framework, the subproblems we solve are min over x, ax minus b, p norm to the p, plus some constant times x minus y. Except now it's the norm is not the p norm anymore on x minus y, it's in a 2 norm. So similarly, a way to think about this is like we're regularizing a bit with the L2 norm so that these subproblems can actually be solved efficiently. And that's where it gets used, that the ellipse is at least as large as the p norm, that you have some, that it's enough regularization and it's not too large because of the upper bound. Very, very high level. That's how you should think of it. But understanding precisely where the 1/3 comes from requires more work. Finally, I wanted to discuss a little bit on how you actually compute the Lewis weights, because I haven't really mentioned that. So there's an exact algorithm for computing Lewis weights when P is less than 4. But we want to handle the case P at greater than 4 possibly, because our algorithm can work for even large values of P. So it turns out, if you remember the analysis, that our algorithm actually only requires what we call a Lewis weight overestimate. Precisely, we just need weights Wi, so the Wi is actually at least this right-hand side, but Wi can't be too large. We still want the L1 norm to be at most 2 times D. So P equals infinity corresponds to computing an approximate John ellipse, which was done. And it was shown to only require a polylog number of linear system solves in matrices A transpose dA. So kind of a very small overhead. Such an algorithm, we show that it directly extends to P between 4 and infinity. And that's how we compute our Lewis weights approximately. And that's sufficient for our algorithm. And yeah. Okay. The other thing I wanted to now mention is how our use of Lewis weights is kind of fundamentally different from previous applications of Lewis weights to p-norm regression. The more standard way to think of Lewis weights are that Lewis weights provide importance measures for the rows of A in comparison to the other rows. So like for example, one of the properties that we use is that AX, the ith coordinate, is not too large compared to the L2 norm, some L2 norm. So like in that sense, the Lewis weights are providing some measure of importance. And then when you know the Lewis weights provide some measure of importance, well, if you sample by the Lewis weights, then that will give you possibly a sparsifier. In other words, AX P norm, in other words, if you try to sample by Lewis weights in some sense, then you can construct a matrix A tilde with less rows than A, hopefully. And A tilde X P norm is always approximately AX P norm, so let's say up to a factor of 2. And such ideas were used in several previous works. It's been known that you can construct such an A tilde with D to the P over 2 rows instead of N rows that A has. So if N is greater than D to the P over 2, then A tilde has less rows. This can be done for any P at least 2, and in fact, it's tight. So let's imagine that our algorithm instead constructs such a matrix A tilde and then runs the previous algorithms on this A tilde, which is an approximator. So the number of iterations would then be D to the P over 2 raised to the P minus 2 over 3P minus 2, which is much larger than just a single D raised to P minus 2 over 3P minus 2, because P can go all the way up to like polylog or like something like that. So this number of iterations is much, much larger. It's like larger by a P over 2 power from our iterations, which are almost always at most D to the 1/3, kind of independent of what P is. So in some sense, our algorithm is doing as well as if A tilde had like a D polylog number of rows, which is actually not possible. A tilde needs D to the P over 2 rows, but our algorithm kind of bypasses this framework of using Lewis weights to do importance sampling and kind of just directly goes for the ellipse approximation that is needed in the algorithm. And that's how we get like D to the 1/3 iterations instead of a much larger iteration count. So now let me briefly mention the P less than 2 case. As a reminder for what the P norm regression problem is, we wish to compute AY minus B, P norm at most 1 plus epsilon times the minimum of AX minus B P norm over all P. And let's do the case P less than 2. Turns out that when you dualize this problem, you can construct a matrix A and B, not necessarily the same as the original matrix A and B. I'm being a little lazy with notation, such that min AX equals, such that you want to compute min AX equals B, X Q norm to the Q, where Q is the dual norm of P, and hence Q is greater than 2. The presence of this linear constraint substantially complicates the type of Lewis weights required. We call them regularized Lewis weights in the paper, and they seem to not be immediately compatible with acceleration methods, like acceleration or width reduction, any of these. However, we still achieve an algorithm which has iteration count O tilde Q times D to the Q minus 2 over 2Q minus 2, which is closer to square root D than the more optimistic cube root D. So now let's conclude. We give an algorithm that does P norm regression in O tilde P to the P times D to the P minus 2 over 3P minus 2 iterations. So this is something like P times the cube root of D iterations. This improves over previous bounds of square root D and cube root N. So the idea behind our algorithm is that we directly use Lewis weights to build an ellipse that approximates the LP norm ball with a reweighted L2 norm ball. And this contrasts with previous approaches that use Lewis weights to sparsify or subsample. And those methods actually cannot achieve a D to the 1/3 iteration count. As for open problems, I think the most natural open problem is to achieve a cube root D iteration count for P less than 2. And this would kind of make this whole picture make a lot of sense for LP norm regression. An idea for doing this is to directly sparsify the residual problem which results from it. So in some recent work, some authors achieve a row count of O tilde D to the 4 minus 2 root 2, which is like D to the 1.2-ish for P norm regression for P less than 2. But this is not all the way down to D, so they don't get the cube root D iteration count. So I think this is a very natural open problem that would give a very nice general picture for what's going on for P norm regression. And another natural question, which is kind of connected to this work, is to give a clean analysis of acceleration using width reduction methods. So this was done in some sense in ABS for quasi self-concordant functions, but I'm kind of just asking in general, can we show a very precise connection between acceleration and width reduction multiplicative weight methods? And yeah, that's the talk.